was. But what if we had another predictor, say age of the customers? It's easy. Companies can get our ages pretty easily. So they could have the age of the customer, the time that they spent on the online chat feature, and how much they spent. So it might be a more powerful model if there's more predictors, right? So that is what we're going to be moving into. And if you test the overall model using the ANOVA, you're basically testing all of them. So here in the simple linear regression, we only have one slope. When we get into multiple linear regression, we're going to have more than one slope. We're going to have lots of slopes, because if you have more than one predictor, you're going to have more than one slope. So we become very multi-dimensional pretty quick. Okay, so you take this, and this f-test is testing, it's equivalent to the t-test for the slope. You're just testing, is the slope equal to 0 or is it not equal to 0? So in this case, you can either use the ANOVA f-test, or you can use just the simple t-test, because it's only one slope, one predictor. But when we get into more than one, then it really comes into play. K is, in this case, the number of predictors. And so it would just be 1. For simple linear regression, K would equal 1. So if one slope, then K equals 1. And remember how all along we've been using n minus 2? Here is why. If you do this, n minus 1 minus 1, that equals n minus 2 when K is 1. So in simple linear regression, K is 1 because there's only one predictor. And n minus K minus 1 is n minus 2. And so we have already seen this. This should be TO. This has an O on it. Some books just have SST just for total. So we've seen these three, but we haven't really used them. The SSE we've seen is the square root of the sum of the square, right? It's the SSE. It's sort of baked into that formula for the standard error of the model. The SSTO is just literally the sum of the squares of the y's. It's just literally this here is equal to the SSYY, right? And if you know any two of those, you can figure out the third. So if you know the sum of the squares of the total, and you know the SSE, so if you know the SSTO and you know the SSE, then the SSR is going to be the difference, because it's going to be SSTO, just like we did before, will be SSR plus SSE, two sources of variation. The variation that is explained by the model added to the variation that is unexplained, that's the error. Okay, so if you know, let's say you know this one and you know the SSE, then you can just derive the SSR, the sum of the squares of the regression. So that's the source of the variation. So the source of the variation from the regression is SSR. The source of the variation from the residuals is the SSE, E standing for error. It's sometimes residual we know is the error. It's sort of like how off are we? Like what's that vertical distance? Y minus Y hat. We went through those to see what those errors were. It's sort of like, okay, here's my data. How far is the model, the line from my data? Because it's going to have some distance there. So we saw that, the sum of the squares of the error. And it's right here. There they are right there. Y minus Y hat and squared. So when you want to get to the mean square error, these are the new ones today. The mean square error is going to be simply, the mean square error is, you can probably guess, it's going to be the SSR divided by K. In our case, just the SSR, because K is 1. And it's just like our ANOVA table. So to get the MSE is going to be the SSE divided by, and you can guess, n minus k minus 1, right? N minus k minus 1. Or n minus 2 if it's just one predictor. And then that brings us to the F value. The F value is the MSR divided by the MSE. And then you get that F value, the F statistic, call it the test. It's the main value, the goal that we're getting. And we compare it to the F critical value from the table. And if it's larger, if our F value is larger, right, then the critical value, we have a good model. This is a way to test the model fully. So if you have more than one predictor, which we will in the next chapter, we will be able to do this global test to see if all of those predictors are significant all at once. Okay. So the SSR, there's a formula there for the SSR. If you have those sums of squares, it's another way of getting them. You're probably noticing now there's different ways you can derive these depending on what you've been given, right? It's algebra at this point, right? A lot of algebra, but it all fits together really nicely like a puzzle. You just want to understand what each of them mean. So the SSR is the sum of the squares of the regression. And then the SSE is the errors, y minus y hat. Just visualize those vertical distances. How good is my data from the model? And then the total is the SSR plus the SST, which it ends up being the sum of the squares for just the y's from the raw data from the y, right? So we know those sums of squares for the xy and the sum of the squares for the x's and the sum of the squares for the y. We know how to derive those from the raw data. Now we can put them all together and put them into an ANOVA table and test the overall model this way. And if we get a significance, if we reject the null hypothesis, it means we have a good model. Okay. The beta naught or the beta 1 is equal to 0 versus beta 1 is not equal to 0. We could just run a t-test, right? We could just do a t-test, or we can run the ANOVA. You have a choice because it's just one slope. So we can, from the table, you can get the MSR. The mean square of the regression is going to be the SSR divided by k, which is 1207.65 divided by 1. It's just going to give us 1207.65. And we're done. The MSE, the mean square error, is going to be the SSE divided by n minus k minus 1, which is equal to 57.56 over 3. So how many data points was there? It must be 5, right? N must equal 5 in this case, because n minus k minus 1 is equal to 3, then there must have been 5, right? And that gives us, what do we get for that? Anybody have an answer? 19. Lots of number crunching today. 19.187. Sounds good. Sounds all right. And then we can get the F value. The F value is just going to be, F is going to equal the MSR divided by the MSE, which equals, so you just take 1207.65 divided by 19.187, 62.941. That sounds a lot like the output, right? Very close. They've rounded, yeah. Mhm. We're not doing multiple regression yet. We're just saying K is 1. When K is 1, we have simple linear regression. When K is greater than 1, we have multiple. But yeah, so I'm setting the stage, getting ready for any K.
Okay.
Yeah. Yeah. So far this is still the same as our online chat feature with just still one predictor. Yeah, we're still in 14. We're still in 14. I just want everyone to get used to the table with one slope, right? One slope, which is one predictor, before we go on. All right. Because this is the coverage for quiz 4. It's going to be all about ANOVA, all about the ANOVA. Okay. Same with the lab and the quiz. So 62.94, we could grab the F table, and what we do here is, what would be the F critical value? I need 2 degrees of freedom. Anyone want to guess what the degrees of freedom would be? What would you use? We need a numerator and a denominator degree of freedom. Just use 1. That's one of them. We need another one. That's the numerator. And then we need a denominator. We use this one. So remember how these were in the denominators, right? Those correspond to the degrees of freedom for the F critical value. So 1 would be the numerator. So I would look at 1 right here. All right. And we want 3. Critical value right there. 10.13. Right? If alpha is 0.05, which it almost 99.999% of the time it is with all these tests for output. So that would be the critical value, 10.13. Let's compare it. So the F critical on 1 and 3 degrees of freedom was 10.13, was it? 10.13? Is it a good model? Want to keep this model? Or do we want to go, nope, not good. The data's not good. We need to get more data. We can go get more data. Or is this good? Remember, if the F is greater than the critical, we keep. Yeah, so this is good. We have significance here because F is greater, that test value, the F value is greater than the F critical. So therefore we reject this, reject that, and we're going to keep this. So reject that and keep the second one. This is good. It means that the coefficient is not equal to 0, right? Just imagine a slope equal to 0, we wouldn't want that model because that means there's no change, right? The slope means change over time, right? Means change. So if the slope is 0, we don't want the model. We reject that the coefficient is equal to 0. We accept that is, right? We accept that it is not equal to 0, and that's good. And what was the estimate here? I'm going to run back. The estimate was equal, this was our B, this was our slope. So it means that, and it's consistent with a small p-value, but it means that that's a plausible value and that 0 is not a plausible value. And we're happy because it means we have a good model. Okay.